All right, folks. Well, welcome back. I hope everyone had a good day yesterday. Hopefully, you were able to work through a few of those problems that I asked you to do, and that way, then we can continue to work on this. What I'd like to do then is I want to go ahead and do number. I asked you to do number 36 in your book, and so I'm going to work out that particular problem for you. That's part of your homework. And so I'm going to work that problem out for you so we can kind of review what we did with the percent yield and what it means and what we can use the percent yield for in terms of calculating for determining formulas. And so I'm going to go ahead and do that. Let's go ahead then. If you have it, go ahead, get it out. If you don't have it, go get the your work from yesterday. And I'm going to go ahead and I'm going to start with number 36A. Okay. All right. Then 36A, they tell us then that there's this compound. This compound that's made up of oxygen and hydrogen. Whatever this compound is, we don't know what the empirical formula is going to be. And remember, the empirical formula is the formula for a compound, the formula of the compound in its simplest whole number ratio. And different compounds can have the same empirical formula. The difference then is with the molecular formula. We'll talk about that in just a moment. But the empirical formula itself, though, is the formula for a set of compounds in which the atoms are related to each other in simple whole numbers. And so we're trying to find what these simple whole numbers are. But with that said, then they have to give us some information about these atoms, okay, about the elements in this particular compound in order for us to find the empirical formula. And so what they do is they give us the percent composition. So in this problem here, they tell us then that we start out with that this particular compound has 94.1%, is made up of 94.1% oxygen and 5.9% hydrogen. So these are the percent compositions, and we were able to calculate for these percent compositions, remember, because if we know the masses or we know the formula, we can use molar masses. The percent composition, the information that it gives us, what it tells us is the amount of each one of these elements, the percentage of each one of these elements in a compound, in this particular compound, whatever it is, okay? All right. And so we had those 7 steps. We had those 7 steps that we used to calculate for the empirical formula. Folks, I don't suggest that you memorize those 7 steps. By working and by practicing these problems here, you'll commit that to memory just by using them, but don't memorize them. Okay, but I'll go through these steps with you anyway. Okay, so there it is. We've identified. So the very first step was identify the percentages, percent compositions, and there it is. So that was the first step. Okay, so the first step in doing the empirical formula calculation. The second step that we're doing is we're going to assume 100 grams. That means that whatever this compound is, whatever this compound is, we're going to assume then that we have 100 grams of it. Okay? The reason for that, it just makes the conversion here a lot easier. Okay, so you can choose any mass here that you want. It's completely up to you. But if you do that, then you have to calculate for the amount, the mass of each one of these elements in this particular compound. If we choose 100 grams, folks, then the percentages then correlate directly to this to 100 grams, meaning then that if you have 94.1% of oxygen in 100 grams, then 94.1 grams will be of oxygen. With that said, then we will have 5.9 grams of hydrogen. So that's step number 2. Assume 100 grams, and then from there, then we have the mass of each one of these elements. Why do we need the mass of each one of these elements? We need the mass of each one of these elements, folks, because we have to find the moles. We want to find the moles of each one of these elements in this compound. We cannot use the masses here because these subscripts here, whatever they are not mass ratios, they are mole ratios. That is the moles of each atom in this compound here, but also the number of atoms as well. That's what these subscripts indicate for us. So that's why we have to do this conversion here. So this is a mass to moles conversion for both of these, which means that we need the molar mass of oxygen here and the molar mass of hydrogen here. So the molar mass of oxygen is 16 grams per mole, and we find that on the periodic table. And so we have to plug it in so that we have moles on top and grams on the bottom. And why do we want it that way? It's 1/16 because the unit of grams of oxygen cancels out. And when you plug that in, you get your answer then as being 5.9 moles of oxygen. Okay? Now do the same thing for hydrogen here. The molar mass of hydrogen is 1 gram per mole. This is the atom atomic hydrogen, not the molecule of hydrogen, which is diatomic. Okay? And so this is going to be 1 gram of hydrogen. Okay, so that cancels out that unit for us, and then we end up here with 5.9 moles of hydrogen. All right, so we're almost there, folks. So what do these numbers tell us? It tells us this, that we have, for every 5.9 moles of oxygen, we have an equivalent of 5.9 moles of hydrogen. So now, I'm sorry, hydrogen. So let me go ahead and erase that. Okay, so now we have the ratio of oxygen to hydrogen. But remember, the empirical formula requires that we have the simplest whole number ratio, and we don't have that here. First of all, this is not a whole number. So we're going to go ahead and divide by the smallest number. Okay. So that's this is going to be step 4 and 5 here. Divide by the smallest number. Okay, and we end up with then O1 H1. Simplest whole numbers there. We can stop right here. We do not need to do the last step because these are already whole numbers. Okay, so that is the empirical formula for this particular compound here. That's the empirical formula based on these percentages. These are the amounts of oxygen and hydrogen in this particular compound. Okay. All right. So please make sure you practice that. I have in my 3 of my other classes, I have an exam. I will be giving an exam on Monday for them. So after school today, if you want to come by, you can. But I'm going to go ahead and I'm going to take their questions first because they have their exam on Monday. But remember, our exam is next week. And so if you feel like you can, again, if you need to come by and ask the questions about empirical formulas here, please come by. I will get to you, but like I said, I have to prioritize and help the other classes first. But I will get to your question. But if you think you can try to work this out and over the weekend, come by on Monday and get your questions answered. Okay. All right. So with that said, then we do have to continue on. We do have to continue on and work on this. Okay. All right. So empirical formulas, well and dandy. But understand this: the empirical formula doesn't necessarily represent a compound itself. Okay, so let's make sure we remember what we did here. Okay, so I introduced you to 2 compounds on Thursday when we started empirical formulas. Okay, and I told you then that these compounds here. So this is acetylene. This is acetylene. That's that welding torch, welding gas. Okay. Okay, so this is acetylene, and then I gave you the formula for polystyrene, okay, that's HC8H8. So this is polystyrene. That's the packing material, polystyrene. Okay, and so those are the formulas for these 2 different compounds. If we reduce this here, if we simplify both to their simplest whole number ratio, okay, the amount of carbon and the amount of hydrogen to the simplest whole number ratio, we get the empirical formula, okay, for both of them. Okay, so both of these atoms here are in a 1-to-1 molar ratio. It's just we have 2 of each here, and this is also a 1-to-1 molar ratio, but we have 8 of these. And so therefore, if we reduce these atoms here and reduce these atoms here to their simplest whole number ratio, we get that empirical formula. Okay. All right. So my question to you then, we learned just now how to obtain this empirical formula here. We just learned how we can get that. If we were given the percentages of carbon and hydrogen, we can get this empirical formula. We know how to get that. So is it possible then, let's say we did not know what the formula is for acetylene. And so acetylene is not C1H1. Acetylene is 2 carbons and 2 hydrogens, not 1 carbon, 1 hydrogen. The question then is, if we start out here, we know the empirical formula, is it possible for us to go back in that direction? That is, if we want to solve for this formula here, same thing here. Can we get that formula? Is that possible if we start out with if we can calculate for the empirical formula? Okay. Well, let's analyze something here. Let me ask you to consider this really quickly. Okay. Let's find then, what's the mass? Let's go ahead and find the mass, and I'm going to erase this really quick room here. So let's go ahead and find the mass of acetylene here. So 2 carbons, 2 hydrogens. The mass here is 26 grams per mole. Okay, So this is the mass of this compound. Okay, let's go ahead and do the same thing for this compound. The molar mass of this compound, which is 8 carbons and 8 hydrogens, is 104 grams per mole. Okay, so this is the molar mass of this. Here, this is a formula, folks, so we should be able to obtain the mass of this particular compound as well, and that is going to be 1 carbon, 1 hydrogen. That's going to be 13 grams per mole, right? So let me make sure you understand this. What we did here is we calculated for the molar mass. This is the molar mass of polystyrene. This is the molar mass of acetylene. This is what we call the empirical mass, because this is the empirical formula, and the mass of the empirical formula then is going to be the empirical mass of that compound. Okay. All right. So my question to you then is, can we, going back to what I have, can we go, if we have this, if we did not know this formula, if we did not know this, could we somehow get to this if we know the molar masses? So now that we have the molar masses, let's compare those really quickly. Let's compare those really quickly. Okay. All right, so let's go ahead and let's take a look at how this works. Okay. So if you notice here, this molar mass is 2 times, this mass here is 2 times greater than this mass. This mass here is 8 times greater than this empirical mass. So the molar mass of polystyrene is 8 times greater than the empirical mass. Okay. The molar mass of acetylene is 2 times greater than the empirical mass. So do you see a connection here? Do you see a pattern here? And I hope you do. And that is this amount here, how much bigger the molar mass of acetylene is than the empirical mass, corresponds directly to those subscripts right there. The how much larger the molar mass is of polystyrene than that of the empirical mass, the 8 here corresponds to that, to the subscripts there. And so to find then what we call the molecular formula, so this is what we refer to as the molecular formula. Okay, to get the molecular formula, which is actually, if you think about it, I use that. You'll see that this textbook uses the term molecular formula in a more generic way, but we should actually consider this then as the actual formula for the compound, to get the actual formula for a compound, because we can use this method here for not only molecules like we have here, but also for ionic compounds. Okay, we can use this method here to find that. Okay, we are actually finding then the actual formula for the compound itself from the empirical formula. And so what do we have to do? We have to find the relationship then between the molar masses and the empirical masses. Find what we call here this multiplier here. So this is what we refer to as a multiplier. Okay. So this is our multiplier. And why do we call it a multiplier? Because we have to multiply the empirical mass to get this molar mass here. But we also have to multiply the empirical formula. So if we double everything here, and we multiply this by 2, we get the molecular formula, or this actual formula. So the goal then, as we move forward to, in the last section of this chapter, is that we need to find the relationships between the molar masses and the empirical masses, and from that we can then go ahead and find the actual formula. So what we're going to do moving forward is we're trying to find this actual formula here. Okay. All right, so I'm going to erase the screen here really quickly, and let's take a look at another example of relationship between molar masses and empirical masses. Okay. So again, this molecular formula is obtained from the empirical formula, but it will have different molar masses because this molecular formula here, and again, which is what we refer to as the molecular formula in the book, and you'll see it happen in other textbooks as well. But we're actually trying to find the actual formula here. So to get the actual formula, we need to know the empirical formula, and we're going to compare the mass of the empirical formula, which is what I called the empirical mass in the previous slide, to the molar masses themselves. Okay, so let's take a look at an example here. Okay, all right. So if you notice here, if you take a look at this, the first one here, this is your empirical formula right here. How do we know that this is the empirical formula? Because simplest whole number ratio. Okay, and so the ratio here is a 1 to 2 to 1 mole ratio between carbon, hydrogen, and oxygen. And it just so happens that this particular empirical formula does represent an actual compound. It's formaldehyde. It's that preservative that they use in biological labs to preserve their specimens. Okay? All right. So let's take a look at this. So that's the empirical formula. So make sure you understand that this is the empirical formula here for all of these compounds. So this is your empirical formula for all of these compounds. Okay, let's take a look at this molecular formula here. So we're told then that we have this compound known as acetic acid, which is basically in its dilute form vinegar. Okay, so we have this particular formula here. This is your acetic acid. Okay, and let's look at the relationship here. Okay, so first of all, if you take a look at the formulas themselves, if you notice then the relationship between formaldehyde and acetic acid, you have to double all of those atoms. You double it. Okay, so the multiplier here is twice. So the formula here for acetic acid is twice as big as that for formaldehyde. You have twice as many carbons, twice as many hydrogens, and twice as many oxygens. Okay, so that's what we have there. But so with that said, let's take a look at the molar masses. So this is the empirical mass here. This is the empirical mass. Okay. And this is the molecular mass of this compound. And you'll notice that the molecular mass is 2 times larger than the empirical mass here. And there we have it. That's the multiplier that we have. So imagine this. If I did not give you, if this was not given to you, if this was not given to you, you don't know what that is, but you are given the molar mass here. If you find this multiplier here, and that's pretty simple, you just use that multiplier, you double the empirical formula, and then you will get your molar mass here. You will get the molecular formula here for this compound. Okay. All right, and we'll work on that in just a moment to get that done. Okay. All right, so let's go ahead. Let's do this again. All right, so let's compare this here. So let's say then we don't know what glucose is. You're not given the formula for glucose, though it is given here, but you're given the mass, the molar mass of glucose. If you know what the molar mass is for formaldehyde, which you can get once you get the empirical formula, if you have this, if you have the empirical mass, you can compare this empirical mass here to the molar mass here. If you notice then that the molar mass of glucose is 6 times greater, there's your multiplier, than the molar mass of formaldehyde, which means then, if you can imagine this, in order to get from the empirical formula to the molecular formula here, we just increase the number of atoms here by a factor of 6. You have 6 times more carbon in glucose, and there it is. 6 times more hydrogen in glucose, and there it is. It's 12 here, and 6 times more oxygen. Okay, so there's your multiplier. You can obtain that from comparing the molar masses, comparing the masses. Okay? All right, very good. So with that said, then let's go ahead and so the molar masses. Then make sure you keep this in mind. Is related to the empirical formula by some factor. Okay, so some factor, and you have to be able to find what that factor is. So the molecular formula of a compound is either going to be experimentally determined, okay, or it's going to be a simple whole number multiple. So that multiplier of the empirical formula. And we can get these masses, so we can obtain these molar masses. These are experimentally derived values by using an instrument such as this here. This is known as a mass spectrometer. And so you don't have to worry about this in this class because the molar masses will be given to you. But like I said, we can obtain the molar masses even if we don't know what the formula is for the compound. We can obtain its molar mass by doing an analysis here in lab. Okay. All right, so in class then, how do we go about calculating for the molecular formula? Well, first of all, we have to determine the empirical formula. If it's not given to us, we have to calculate for it. And in order to calculate for it, we have to have percent compositions, and so we calculate for it. And then you want to find the mass of that particular formula. Okay, so remember, this is what we refer to then as our empirical mass. Okay, so this is the empirical mass. Okay, so this mass of the formula here, this is your empirical mass. You have to calculate for that. So that's your empirical mass. Okay, all right. You get the molar mass of the compound, which will be given. This will be given to you in the problem, so you have to make sure you can identify it. Okay, divide the molar masses, get that multiplier, and then from that you can find then the formula, the molecular formula for the compound itself. Okay, all All right, so let's go ahead and let's take a look at an example of a problem here. Again, I want to work out this problem with you. Okay. All right, so in this particular problem here, let's go ahead and identify what we're given. Yeah, I'm running a little low on time. Okay, they tell us the molar mass. Okay, so here we're given the molar mass of this compound. So they want us to find the molecular formula. Okay, so what is the molecular formula of this compound? We don't know, but we do know its molar mass. So the formula has that molar mass. Okay, and then we are given the empirical formula for the compound. Okay, and so we don't have to solve for that. Okay, and so with that said, then let's go ahead. The first thing we have to do is we have to calculate for the empirical mass. Okay, okay, so the empirical mass here. So for C carbon, this empirical formula here, which is 1 carbon, 4 nitrogen, 4 hydrogens and 1 nitrogen. You add all those up because that's going to be 12 grams per mole plus 4 times 1 gram per mole plus 14 grams per mole. Okay, and so we get an empirical mass here of 30 grams per mole. Okay, so this is the empirical mass. This is the mass of this particular compound here. Okay, what we're trying to find, folks, we're trying to find then is what is the formula for a compound that has carbon, hydrogens, and nitrogen in it, but not in a 1 to 4 to 1, but if you reduce it, it'll be 1 to 4 to 1. But the actual atoms here will not be 1, 4, 1. Okay, and so what do we know about this molecular form, this compound here? We do know its mass. Okay? We're given this mass here of 60 grams per mole. We know then that whatever this compound is, when you add up all of these atoms here, whatever they are, it will equal 60 grams per mole. And so if you compare that, okay, you compare that to the empirical mass here, which we just calculated for, the mass of the actual compound itself is 2 times greater than the mass of the empirical formula. And so there it is. There is our multiplier, which means then we have to double everything here to get our answer. Okay? So we take carbon, there's twice as many carbons in our, so this is our molecular formula. That's the actual formula. Okay, so what did we do? We just went ahead and doubled everything. So we have that formula. Okay. We doubled the number of carbons to 2 here. We have doubled the number of hydrogens to 8 and doubled the number of nitrogens to 2 here. Okay, and so that is our molecular formula. Okay, okay, very good. So with that said, then what I'd like you to do, and we'll save this here. I'll clear the drawings here. What I'd like you to do to finish out the problem then is I want you to go ahead and try number 31 in your problem set. Okay, so this is the last problem that I'd like you to do. Show your work on your paper, okay, and then submit that. And I will start with this problem for you on Monday. Okay, so go ahead and work this problem out, folks. Come on by and see me after school today. If you have any questions on it, go ahead and try this. Make sure you submit your answer on Edpuzzle, and then make sure you upload your work onto Classroom. Okay. If I don't see you this afternoon, folks, have a good weekend, and I'll see you on Monday. Okay.